Welcome back, ladies and gentlemen. Here we're talking about Newton's second law of motion. Something I want you to keep in mind throughout the study of Newton's laws. We're basically talking about forces, and the reason why is what Newton was very concerned with. Why does certain motion exist? Why do objects change their motion? What is the cause of all these things happening the way they do? When we were studying kinematics, we were looking at what was happening, what direction was the motion, how fast, how long did it take, what was the rate of change of the velocity. Now we're looking at why those changes or why those motions existed. Now, Newton's second law, dealing with forces, in the simplest sense, basically Newton was saying that unbalanced forces change motion. In other words, forces cause accelerations. If you look at, let's look at an example. If we have just whatever object we have, and, well, what are the forces acting on this object? We have weight, pulling straight down. There is the support force, or the normal force, pushing straight up. And let's say we're going to apply a force to it to the right. That. Well, what we know is going to happen is there will be an acceleration because this guy is an unbalanced force. So we will have an acceleration in that direction. The acceleration will happen always in the same direction as this thing called the net force, the overall force. If you look at this, well, it kind of makes sense. Forces are vectors. We have to add the vectors together. So off to the side here, if I imagine adding the weight, which is there, and I add the normal force, which is going to be there, well, what do I get? Those two cancel out. But there's nothing canceling out the applied force right here. And so we will produce an acceleration in this object. If there's nothing else happening, then that's nothing else affecting the object, then that's what's going to happen. We write this by simply saying the net force. Well, this thing called the net force, it's the overall effect of all the forces combined. What that means is we have to sum up all the forces, literally all of them, and, well, in this case, very specifically, the net force will equal that applied force. Okay. Well, from this, we can say the block will accelerate in the direction of that net force, which is our applied force. They are equal. Well, imagine this. Now, I'm gonna alter the situation just a little bit. Same object though, sitting on the same surface. Let's imagine a friction-free surface. I mean, that really doesn't ever happen. But for now, let's just make believe. Same weight. Same normal force. We're actually going to learn about normal force and weight and also friction later on. But now, what I'm going to do is I'm going to change the force that I apply. Remember, I had this one, so here was the original force, and I'm going to double it. I'm going to take it from there and double it. So I have 2 times that applied force. Okay, well, what's going to happen to the acceleration? Let's find out. Turns out, I'll just use the same color. If we double the net force, then that leads to doubling the acceleration. 2 times the acceleration. So we will experience, the block will experience twice the acceleration. In the same direction as before, we have the net force, the only thing that's unbalanced, right here. And so from that, now we can say that the acceleration the object experiences is proportional to, directly proportional to, the net force. Okay. Testing has confirmed this. It's been well established. Well, that's good, but that's not quite enough. We know that if we double the net force, we will produce twice the acceleration. If we triple the net force, we will produce triple the acceleration. But that's not the only thing that affects the acceleration of an object. If I have a rolling cart here, you might recognize this, and I try to push on it, I apply a force to it, I can get it to accelerate. Fine. And it has a certain mass. If I change the mass, I make it more massive, that same force does not produce the same acceleration anymore. The acceleration was reduced. And so it turns out, when we're dealing with this stuff, that the mass of the object has an effect on the rate of acceleration as well. More massive objects have more inertia. If you remember this word inertia, meaning laziness. This is kind of like Newton's first law of motion, right? Well, how lazy was the cart here compared to how lazy was it here? How difficult was it to get that thing to change its motion compared to how difficult is it now to get this to change its motion? And that's basically what we're talking about. More massive objects are harder to motivate to change what they're doing. That's what Newton's first law says, inertia, or a little reference to the first law. So mass affects the rate of acceleration of an object also. If I apply the same force to the more massive object, I don't see the same acceleration that I did before. Yeah, there we go. Same force, you can see it will accelerate a little faster. So what we know is that acceleration is proportional to the inverse of the mass. If you increase the mass, well, then it's harder to accelerate the object, so for the same force you get less acceleration. What this means for us is that when you combine these two effects, we have the acceleration of an object is really going to be equal to, and this is something that Newton worked out, the net force divided by the mass. Lowercase m for mass, not meters, but mass. Now, this is not the original way that Newton wrote or expressed this relationship, but it works for us right now, and it is accurate. You may usually see F equals ma. Now, you can write it like that, that's fine. But the beauty of writing it this way is that the acceleration is the result of two different things happening. You have a net force, an unbalanced force, acting on an object, and the object has mass. And the combined effects of these two lead to an acceleration. If all of the forces are balanced, then you have zero net force and you'll have zero acceleration. Okay. If you have a very, very small net force, you will have a very small acceleration. If you have a very large mass for a given force, you'll have a relatively small acceleration. But if you lighten the object, if you reduce its mass, and you can apply the same net force, well, then you will get a greater acceleration out of it. Imagine race cars. They want to build those as light as possible because they want those cars to accelerate as fast as possible. So they reduce the mass of the car, and a huge amount of engineering goes into that. And they also try to boost the net force. They make the engines very, very strong, and they will produce very, very large accelerations. Okay, well, that's all well and good. This basically is right here Newton's second law of motion. How do you determine the rate of acceleration that will affect, by the way, that is also a vector. Your book will sometimes do that. How do you determine the rate of acceleration of an object? Well, you have to know the net force acting on it, and you have to know its mass. That's why. This is why the acceleration happens. Okay, let's look at an example. Here we go. This is by the way, one of the problems out of the textbook, I should note that for you. This happens to be page 140, number 6, I believe. We have this 92 kilogram water skier, so we're given mass. Floating in a lake is pulled from rest. So there's mass. Pulled from rest, that's probably important. To a speed of 12 meters per second, that sounds like a speed we'll need. In a distance of 25 meters, so more information there. What is the net force exerted on the skier? So we want to find net force, assuming acceleration is constant. Now, okay, constant acceleration is a kind of thing we can assume for just about all of our situations here in this course. First thing I want to do is a quick sketch, right? And water skier. I'm terrible at this, so we have water ski, hold on to the rope. Well, from rest, and we know that, so from rest, so initial will be 0 meters per second. And we're going to have a distance of 25 meters. And we have a final velocity over here. And we're told that to a speed of 12 meters per second. Okay. And so now, listing my information. Don't skip these steps. Don't skip. Don't get lazy. Initial, 0. Final velocity, that's supposed to be an equal sign, 12 meters per second. It's supposed to be an S. I know a distance, so a displacement in the horizontal direction, 25 meters. What else do I know? I know a mass of 92 kilograms. Okay, and what do I need? I'm looking for the net force. Okay, so right away there's something you should notice from Newton's second law. If you're going to find the net force, so rearrange the equation to look like this, well, we have the mass, we will need to find an acceleration here. So this is sort of an intermediate step. I know that these two things are linked through the rate of acceleration. I will also need to find that in order to solve this problem. Do I have enough information to do that? Well, step one, I'm going to find A. I'm going to find acceleration. Okay. And if I look at this, I have an initial final velocity, I have a displacement, and I need an acceleration. There actually is one of your big 5 kinematics equations that you can use to do this. So it's, you have your final squared, and I'll go ahead and use the F and the I this time. So equals your initial velocity squared plus 2 times A times your displacement. Brilliant. Let's rearrange for A, and you get final squared minus initial squared, and you're going to divide by 2 times your change in position. Plug in numbers, and solving for A, you're going to get 2.88 meters per second squared. Okay, well, brilliant. So now it's real easy. I can now find the net force. Find F net. And so I'm just going to use F net equals mass times acceleration, and my mass was 92 kilograms. My acceleration is now known, 2.88 meters per second squared. Sorry if this is going off the screen. Let me get this in view for you. And the net force, come on, paper, cooperate, is, when you do the math, 265, depending on how you round, newtons. Okay, forces are measured in newtons, named after Isaac Newton, of course. So this might be worth noting at this point. What is a newton? Here, I don't quite have much room there. 1 newton. When you look at this, you have kilograms times meters per second squared. That's exactly what a newton is. Newton is 1 kilogram meter per second squared. And so it just comes from your mass times your acceleration. That's really what it is. And we combine those, we call them newtons. Newtons is the measure of force. 1 newton is about the weight of a typical apple. It's roughly a quarter pound. So if you had, for your own reference, how large is a newton? It's not very large. Go to the supermarket, typical apple, about a quarter pound. Here in Earth's gravitational field, check this out. What is the rate of acceleration? Here it's 9.8, 9.81. So how much force is exerted by you could say 1 kilogram. Well, you'd have to do 1 kilogram times that 9.81 meters per second squared, and therefore you're getting this thing called the weight. Now 9.8 newtons, 9.1 newtons. That would be the weight, for example. Converting from mass to weight, you have to know the gravitational field that you're in. Okay, enough of that. Just wanted to look at a few things basic to Newton's second law. And so what do we know? What's the best way to express Newton's second law? It's actually this way, as far as we know at this point. Although you will often see it expressed as F equals ma. We're going to use this a lot. This relationship is the foundation for lots and lots of things happening. All right, that's enough for now. Thank you for watching. I'll catch you next time.